Crime exists everywhere, and crime rates are often linked to various socioeconomic factors, including economic inequalities, racial and ethnic disparities, and levels of police intervention. Prior studies suggest that socioeconomic disadvantages strongly correlate with elevated crime rates. Hence, understanding these relationships enables policymakers to design targeted interventions. Despite extensive literature, ambiguity persists regarding how operational policing strategies, specifically the deployment of officers to patrol duties, interact with economic factors to influence crime. Quantifying these relationships is critical for evidence-based resource allocation. If patrol deployment proves impactful, it could validate investments in visible policing. If not, it would necessitate exploring alternative strategies. In this study, we will focus on answering the following research question. To what extent do poverty rates, unemployment rates, and police patrol deployment rates predict total crime rates across U.S. states? In this study, we used the Communities and Crimes Unnormalized dataset from the UC Irvine Machine Learning Repository. For our purposes, we select a subset of variables from this dataset to be used. The response variable total crimes per 100K population is computed by adding the variables violent crimes per 100K population and non-violent crimes per 100K population from the original dataset. For the predictors, we have 4 variables. State is a categorical variable. The continuous variables include the percentage of people under the poverty level, the percentage of people 16 and over in the labor force and unemployed, and the percent of sworn full-time police officers on patrol. Since our research question is about the prediction of total crime rates across U.S. states, it is relevant to include the categorical variable state as one of the predictors. Before working with the data, all rows that contain missing values are excluded. We begin with the following initial multiple linear regression model, where state ij equals 0 for the reference state of Alaska, and the beta 1j's are differences in crime rate from Alaska for each of the state when other predictor values are held constant. The summation index is bounded above by 38 because we have a total of 39 distinct states in the clean data, meaning that we need exactly 38 dummy variables. Note that the District of Columbia is included as a possible value for the variable state by the original data, even though it is a district and not a state. Now we check for multicollinearity issues among the predictors. From the plots and the VIF values, it is clear that poverty rate and unemployment rate are correlated. Other pairs do not show any correlation. Given the observed multicollinearity between poverty and unemployment rates, we expand our model to include an interaction term between these variables, yielding our final model. For each state other than Alaska, we test to see if there is a statistically significant difference in crime rate between that state and the reference state of Alaska. Additionally, we test whether each of the other predictors has a statistically significant impact on the prediction of total crime rate. The significance level used for all tests is 0.05. We further proceed by performing assumption diagnostics. From the residual plot, we see that the residuals do not show any curvature pattern, indicating that the linearity assumption is not violated. However, it is clear that the constant variance assumption does not hold, and we confirm this by performing the Broich-Pagan test. The p-value of 0.01 indicates that we have non-constant variance. For the normality assumption, we construct a histogram of residuals, and it looks like the normality assumption is not violated. Lastly, we check for outliers and influential points, and check if transformations are necessary. From the partial regression plots, it looks like transformations are not needed. However, there do appear to be some influential points and outliers, as this is confirmed by the Cook's distance plot, although these points do seem to cancel out. Due to the violation of the constant variance assumption, it was tempting to use the weighted least squares method. However, this method gave poor results. Therefore, we turn to the bootstrapping method. This method involves creating 1,000 replica data sets by randomly sampling our original data with replacement, preserving both the sample size and state factor structure. For each replica dataset, we refit our complete regression model. From the resulting 1,000 coefficient estimates for each predictor, we calculate robust standard errors as their standard deviation, determine 95% confidence intervals using the 2.5th and 97.5th percentiles, and establish statistical significance when these intervals excluded 0. These are the results of our hypothesis tests. Let's interpret these results and compare our findings with this study conducted by John Bothos and Stelios Thermopoulos. Poverty rate showed a significant positive relationship with crime rates. A 1% increase in poverty correlates with approximately 393 additional crimes per 100K population. This aligns with the paper's finding that poverty creates desperation and reduces perceived risks of criminal consequences. Unemployment rates showed non-significant main effect since the confidence interval contains 0. This counterintuitive result matches the paper's discussion of how high unemployment rate reduces crime opportunities as people stay home and own fewer valuables. The poverty-unemployment interaction term shows significant negative interaction. This is likely because high unemployment rate mitigates poverty's crime-inducing effect. This supports the paper's observation that economic distress reduces vulnerable targets and outdoor activity. Percent of sworn full-time police officers show non-significant effect since the confidence interval contains 0. This contrasts with the paper's emphasis on policing effectiveness. It suggests that patrol presence alone is insufficient without targeted strategies. Finally, the figure on the right shows that significant variations exist among the states. This aligns with the paper's finding that localized factors such as gang activity and policies critically influence crime. Our choice of poverty and unemployment predictors strongly aligns with the reference paper's conclusion that economic factors are primary crime drivers. However, we diverged by including police patrol presence instead of the paper's efficiency metrics that is measured via arrests per officer. This explains our non-significant result versus their strong deterrent finding. Notably, our detected poverty-unemployment interaction extends the paper's framework by showing these factors don't operate independently. High unemployment rate mitigates poverty's crime-inducing effect by reducing opportunities. Based on our study, we conclude that poverty reduction should be the primary policy focus. A 1% poverty decrease may prevent approximately 393 crimes per 100K people. Unemployment programs should distinguish between short-term relief that reduce immediate crime opportunities and long-term solutions that prevent poverty-driven crime. Key limitations of this study include omitted education variables. School dropouts were significant in the paper but unavailable here. Another limitation was using patrol presence rather than police efficiency metrics. There wasn't a variable for total number of arrests in the original data that could be used for measuring police efficiency. Hence, future work should involve integrating education and demographic data and using arrest-to-crime ratios to measure policing effectiveness. For assessing our model's performance and generalizability, we used cross-validation, which confirmed moderate but inconsistent generalizability. The tenfold cross-validation showed acceptable explanatory power with an R-squared value of 0.5, but high prediction error with an RMSE value of approximately 2,274. This suggests our model explains structural relationships, but has limited predictive accuracy for individual communities, which is likely due to unobserved local factors such as gang activity and drug markets. The high RMSE implies real-world implementation would require supplementary local crime audits to identify community-specific risk factors beyond our state-level predictors.